Hi everyone. So let's get started with lecture 11. So in this lecture, we're gonna look into the guts of what comprises a branch and cut or even an MIP solver as we have been using in the course. And as we'll see, an MIP solver is basically a collection of many techniques or many parts. Um, so we're gonna focus on these four main ones, which is more or less common to all of them, and also try to point you out to perhaps some differences that they might have, and how these things interact. But before we talk about what are these, let us first look into what do I mean by a MIP solver. So it turns out that when we think about MIP solvers, I mean the code that is readily available to be called in order to solve your optimization problem, be it linear, mixed integer linear, or even non-linear. What you're actually doing is calling this intricate collection of techniques that are employed in combination to try to give you a solution. I am highlighting here the logo of three companies that I know that make professional grade solvers, especially for MIP. I'm not benefited by any of them by any means. It's just these are perhaps the ones that have been longer in the market, so they have more um, uh, tradition, I would say. So IBM is the maker of Cplex, or the owner of Cplex. Afine makes a solver called Express, and Gurobi, perhaps the youngest of these three, makes a solver that is also called Gurobi. So here are some names for you to Google a bit and learn a bit more. And one impressive thing about these commercial solvers is that the range of speed up that has been observed in the last few years is formidable, without the lack of a better word. You can see that in some cases the speed ups are the order of 50 times in 15 years. So that basically means that more and more is becoming possible for us as optimization practitioners to solve models, to solve problems that weren't possible 10 years ago. Meaning that more and more optimization is becoming much more of a reality in terms of being a practical tool for supporting decision making, planning processes, you name it. The main difference between these or perhaps some open source solvers that are out there as well is that each of them have their own tricks, have their own techniques being implemented, and some of them, for obvious reasons, because these are all commercial products with intellectual property considerations, they are not, you can't really see, they're not entirely fully disclosed. They all somehow are based on the same principles, which is what we're going to look into this lecture. So everything I'm going to show you to some extent is available in all of those. So it's sort of standard per se. But each of them have their own options and have their own components that make them different from each other. And the development of MILP solvers is a really exciting area for research and development. So these companies, they are known for employing PhDs and researchers in the realm of optimization. And they are constantly working towards implementing new methods, implementing new techniques, or making the currently available ones more efficient. So it's really, really, really exciting to see every time that one of those companies are releasing new versions of their solvers, and have a look and see what there is new in there and what sort of speed ups they have been obtaining in terms of solution times for reference instances. So what we're gonna do here, or our main objective with this lecture, is kind of to wrap up this process that we've been looking into since lecture, I want to say 8, that you have a awareness of what is going on behind the curtains when you use an MIP solver, and be aware that there are parameters that can be used to tune, because these solvers, even though they have methods and ways of trying to infer what would be good parameters such that they work in a general setting, there is always the possibility, quite often at least, the possibility to exploit performance benefits if you know what you're doing, and if you know, say, that your problem has a specific property or a specific aspect that you can exploit by setting appropriate parameters, or tuning the solver accordingly. So we'll see what parameters are these, and how some of them work at least. So here is a picture that I got from the one from Cplex specifically, but FICO and Gurobi will have a similar plot to show with a very similar tendency. It just so happened that when I Googled, that was the first one that came up. And so you can find these statistics for pretty much most of the solvers out there. And this is showing the following. So the blue bar is showing the number of timeouts. So whenever this is trying to solve so there is a collection of instances comprised by 5,118 models that is used as reference every time IBM releases a new version of Cplex. So this one here is testing 12.10, the release 12.10. So out of the 5,100 and so models, you said, version 12.2, which is probably 8 years ago, I think. I think these are every year, even though there is a jump on 12.3 here. You see that there's more than 300 instances timed out with a time limit. They probably say somewhere 10,000 seconds down there. And you can see that more recent versions have, you only see now timeouts just shy of 100 of them. And then when you scale the models in terms of how long they take to solve, models that you solve in 10 seconds, up to 100 seconds, and up to 1,000 seconds, those lines, they're showing speed ups in terms of the reference point, which is version 12.2. So you can see that version 12.10 has for larger models have speed ups of the order of 7 times. And that's if I'm not mistaken, is a time span of 10 years, or just shy of 10 years. You can check when 12.2 has been released and let me know. And you can also see that it's a pretty standard computer. Not a bad computer, but not unrealistically good. So this is a sort of progress. You see, Gurobi you can find a plot similar or even better for Gurobi and for Express, FICO Express as well, because this is a common thing. This is what they share. They have these technological developments being employed with really state-of-the-art methods to every year push it a little more, how further they can go in terms of solving challenging mixed integer linear programs. So it's a very exciting time to be alive in terms of MIP technology. So a MIP solver has a flow chart that kind of look like this. This is a simplified version of the things. There are some boxes here that I'm omitting on purpose to make this sort of digestible. That is certainly the common boxes that you'll find for every solver, but it could certainly be a bit more complicated if you take into account other things that we're not going to be discussing. But typically it goes like this. You give your problem to your MIP solver, and then what it does, first of all, it has a pre-solved phase, which is what we're going to discuss next. Basically applying methods to see if there is ways to reduce the size of the problem in terms of number of variables and constraints. And sometimes the pre-solve method is so good that you can immediately find a solution just by doing pre-solve. So you return and that's it. Otherwise, what you do then, you have a node selection, selecting what subproblem is going to be solved. That the subproblem then has its LP relaxation solved. And then you can see that there is these two arrows that saying that basically what happens is that LP relaxation might serve as information for a cut generation, which then can be sent back and having the LP relaxation resolved. So this loop here is a cutting plane approach, kind of like what we see in lecture 9. But there is also this loop towards an heuristic, because it might be so that once you solve the LP relaxation, you can use that information to apply an heuristic and perhaps generate further cuts from the heuristic you generated. For example, there could be things like local searches and all that. So this is a complicated sort of a flow that repeats a few times, and then eventually the problem gets arranged, and then you go to a point where you do node selection. And these heuristics, by the way, I put them here, but they can be actually everywhere. They can be associated with presolving, they can be associated with branching, but we'll see what they mean in this context. And then once you're done, eventually you return. So that's kind of, you can see that it's a combination of branch and bound and cutting planes and much more. By the way, this combination of branch and bound with cut generation is what is known as branch and cut. So if you ask what method this solver is implementing, the generic sort of statement is, it's doing branch and cut. Okay. All right, so basically what we're going to do today is, in the next videos, is look into some of these boxes, in specific the presolve box, the node selection and branching box, the heuristic and the cuts box. And you know exactly what LP relaxation is, right? And hopefully that will become a bit more clear how these things interact. All right, so I'll stop here as an introduction video, and then in the next video, we'll look specifically at the notion of presolving a problem. So see you in the next video.